Today we're going to take a look at the first half of section 3.4, which is multiplication of whole numbers. And we're going to start with the definition. For finite sets A and B, if the number of items in A is A and the number of items B is B, then if n does not equal 0, then n times A is A plus A plus A plus A plus A, whatever, n times. And 0 times, if n is equal to 0, then 0 times A would equal 0. And then if A dot B, A times B, is the number of items in the cross product, or the Cartesian product, we've seen this before, then the number of items in A times the number of items in B is the number of items in the Cartesian product of A and B. All right, so the first thing we're going to do is we're going to take a look at 4 different models for multiplication of whole numbers. The first model is the repeated addition model, and this is kind of where we usually start with the idea of multiplication. What is multiplication? Well, it's repeating the number, adding a whole bunch of times, right? We saw this with Gauss, right? With Gauss's method, the whole way to simplify the process is by getting the same number added to itself a whole bunch of times instead of different numbers. So this is an example of repeated addition. Giselle takes 3 tests every Friday. After 4 Fridays, how many tests has she taken? Right, so if we were not using multiplication, we would think about this as adding 3 plus 3 plus 3 plus 3. Right, so this is 3 times 4. And of course, that would end up giving me 12 tests. So the idea with this model is that we have repeatedly added something a whole bunch of times. Another model, which is not repeatedly adding something, is an array model. Again, used for sets. Minhu is baking cookies. He is able to place the dough 3 cookies wide and 6 cookies long in his pan. How many cookies will his pan hold? Now, I'm sure you've seen lots of things that are put into arrays. So if we were to make, still dotted from last time. Make our cookies. In fact, I'll even make our cookies look more like cookies. Maybe I can make them bigger. Let's try. There we go. 6 cookies wide. 3 cookies, or 6 cookies long, 3 cookies wide. So we have a 3 by 6 array. So of course this makes 3 times 6, which is 18 cookies. And you've seen lots of things in arrays. So you might think of some objects that you're familiar with being in arrays, because in a minute here you're going to create your own word problem example. Very similar to arrays are areas. So area models are like arrays but used for measurement. And here's an example of an area model. Alexis is planning a garden. She has space that is 5 feet wide and 7 feet long. How much area does she have in which to plant? Right, so like a corresponding array model for this might be that she has flowers. She has space for 5 flowers wide and 7 flowers long. How many flowers does she plant? But this is actually measuring space, not numbers of flowers. So in terms of a picture, you might picture that we have something like a rectangular array, right? And then it's 7 wide. And that's not quite going to give me what I need. Let me shift them a little bit. I need 7 wide. 7's really hard to subdivide things into, folks. I mean, just telling you right now. 8, that'd be great. I should have done 8. That'd have been better. Okay, so there's 7 wide. And it's supposed to be, or 7 long, and then I need 5 wide. So here's 1, 2, 3, 4, 5. All right, so I had 5 wide, 7 long, and I can mark it if you wish. So here's my 5 feet. And here's my 7 feet. I'm kind of running into my own words. And of course, we'd have 5 times 7, which is 35. And when we have feet times feet, that's square feet. And it looks like that when it's written, feet with a little 2 above it, but it's called square feet. Okay, our last model, and this is a new one that they've put in this year, but it actually is a really good one, and it ties in really nicely into proportional statistical reasoning. So it'll be a wonderful byproduct of being able to talk about it again at that point when we get to there, and all of you probably have to take that class as well. So it's called Cartesian Product, and it's used for ways of choosing options. So here's an example. Unique is at a pizza place. She can choose from 2 types of crust, thin or original, and 3 types of toppings, pepperoni, sausage, and ham. How many different types of pizza could Unique choose? So this is a Cartesian product because of the choices that she has to make, and I can show you how we think about options with choices. So we're actually going to draw something called a tree diagram. You may or may not be familiar with these. Her first choice is that she has to choose either a thin crust or an original crust. And then no matter what choice she makes, she has 3 choices of toppings. I just barely have enough room to write all this on my screen. So her 3 choices of toppings are pepperoni, sausage, and ham. But she has the same 3 choices even if she chooses the original crust. So we have pepperoni, sausage, and ham. And if you take a look at the branches here at the end, this tells you that there are 6 different pizza options. And that happens because there were 2 options to begin with, times 3 options secondly. So that gives us 6 types of pizza. All right, so what you're going to do now is you're going to push pause, and you're going to create 4 examples, one of each of the 4 types of word problems for repeated addition, array, area, and Cartesian product. And once you've done that, go ahead and hit resume, and you can move on with me to the next part of the lesson. All right, welcome back. So what we're doing next is we're taking a look at the properties of whole numbers. Now, we did properties of whole numbers for addition. We also did them, or we at least looked at them for subtraction and talked about the fact that there just aren't any that hold. Super unfortunate, but it is reality for whole numbers with subtraction. And now we're going to take a look at them for multiplication. And what you'll notice is that we have the first 4 that look very much like the 4 we had before, and we have 2 additional properties that are new for this material. The first one, the closure property. The closure property says that for all whole numbers A and B, A times B is a unique whole number. And we talked about this with addition, right? If I take 2 whole numbers and I add them, I get another whole number. Well, same is true for multiplication. If I take 2 whole numbers and I add and I multiply them, right, then I get another whole number. And again, this is unique with multiplication. It didn't work with subtraction. It did work with addition, but it's also unique to whole numbers specifically, right? So even numbers would work for this. An even number times an even number is an even number. Now, we saw even numbers work for addition. Even plus even was even, but then it fell apart for odd. Remember, odd plus odd is not odd. But the reality is it works for this one with odd as well. Odd times odd is odd. So it really matters what number system you're working with or group of numbers and what operation. The second property is the commutative property. So the commutative property says that the order of multiplication, just like for addition, doesn't matter. A times B equals B times A. So when I was working most recently with my 10-year-old daughter on this is what was happening, right? So we do her multiplication tables, and zeros, ones, twos, they're all easy. She's done those for a really long time. 3s, 4s, 5s. When we get high enough, what ends up happening is that yes, there's more difficult products, but there's fewer of them, right? So when we get to the 8s tables, well, she's already multiplied 8 by everything smaller than 8. She already knows 8 times 7 because she did the 7s tables. She already knows 8 times 6 because she did the 6 tables, right? But once she gets to 8 times 8, she only has a few new ones to memorize. 8 times 8, 8 times 9, and then in her case, her deck of cards, so to speak, went up to 12, so 8 times 10, 11, and 12. But fewer of them to memorize the higher you get. Another property that whole numbers have is the associative property. All right, so the associative property, it will also hold for multiplication, and you'll notice the A, B, and C in the same order, right? A, B, C on the left, A, B, C on the right, but the grouping is the A and the B on the left, whereas the grouping on the right is with the B and the C. All right, the additive identity property is the one we had before, but this is actually going to be the multiplicative identity property, and it matters because the multiplicative identity element is actually the number 1, whereas the additive identity element is the number 0. So the number 1 is unique because when you multiply it in either direction by the number a, so a times 1 or 1 times a, it leaves the a unchanged. So that's the identity property, the identity element being the number 1. These are our two new ones. They didn't exist before at all. So the first one's called multiplication property of 0. It says that when we multiply by 0, again, in either order, a times 0 or 0 times a, we get 0. And then the distributive property involves both multiplication and addition, or multiplication and subtraction. And what you might sort of remember is this idea of drawing, arrows over across for distributing the a through. So a times the sum of sum of b plus c is ab plus ac, or you can do the difference. All right, so our example that comes up next is actually identifying which of the properties are present in each of our values, or each of our statements. So the first equation says 5 times 4 in the parentheses times 0 equals 0. So when we multiply by 0, this is the multiplication property of 0. Our next one says 7 times the quantity 3 times 4 is equal to 7 times the quantity 4 times 3. Now don't get too overzealous and think that just because there's parentheses that it has to be associative or has to be distributive, right? We need to look at what's really taking place. And what's really taking place here is that the 3 times 4 changed to 4 times 3. And so what happened really is that this is the commutative property. Whereas on C, the 734 is all the same. But what actually changes is the values, what's located inside the parentheses here. Here, it's 3 times 4, whereas here, it's 7 times 3. So the values are in the same order, but the grouping is around different values, which makes it the associative property. On D, we have 3 times 4 times 1 is equal to 3 times 4. That's actually the multiplicative identity property. Oh, on E, it's 3 plus 4 times 5 is equal to 3 times 5 plus 4 times 5. And what you'll actually notice is that this is distribution property in sort of reverse order, but that's okay because addition and multiplication are both commutative. And so this is going to be distributive. And it's distributive of a multiplication over addition. And our last one on F says 1 plus 2 times 3 plus 4 equals 1 plus 2 times 3 plus 1 plus 2 times 4. And it's not asking you to clean things up or simplify, right? But it's asking you to recognize that it's taken this quantity 1 plus 2 and it's distributed it to the 3 and to the 4 individually. So this is another example of the distributive property. All right, we're going to do one more example, and then we'll pause for today. It's example number 3. Example number 3 says, JJ claims the following is true by the distributive law, where A and B are whole numbers. 3 times A times B equals 3 times A times 3 times B. How would you help him? So I hope that the first thing that you notice is this isn't distributive. And the reason it isn't is because if you take a look back over here, the distributive property is distributing multiplication over addition or subtraction, and there's no addition or subtraction here. So the first thing that I might talk to him about is that distribution involves addition or subtraction. but this is only multiplication. So the reality is that this is actually just, so we actually have the associative property. Namely, if we started out with what's on the left, which is 3 times A times B, if you want to rewrite it, you could regroup the 3A together and then times B like that. That is a possibility of rewriting this that would be appropriate. Another thing that might be pertinent to talk to JJ about is why this doesn't work sort of from a concrete numerical perspective. For example, so we could show him some version of this. So I'm going to give you an example of one. 3 times 4 plus 7. So if I were to simplify the algebra of this with the addition first and then the multiplication, this would be 3 times, I'm sorry, not plus 7. That was supposed to be times 7 to match what his problem originally started with. So this would be 3 times 28, and 3 times 28 is 84. But if his property, his example, actually worked, then it would have to be that this is equal to 3 times 4 times 3 times 7. Well, 3 times 4 is 12, and 3 times 7 is 21, and 12 times 21 is actually 252. And these two quantities are not equal. So you could actually show him a concrete example as well of it not working the way he expected. So we will pause right here for today. When I'm back on Monday, we will pick up with properties of exponents.